heat transfer from a fire tube. A fire tube, flame inside a tube of a pipe surrounded by process fluid. Okay. So, the heat will be transferred using radiation, convection from fluid to inside surface. Okay. One pipe is here. So, initially it will be reaching to wall, radiation and convection. Okay. So, when radiation is happening, it will not be heating up the fluid, rather it will be heating up directly solid. Okay. So, radiant convective heat transfer from flame to inside surface of the tube, then conduction will be happening after that. From inside metal there will be conduction. Okay. So, after conduction again there will be convection if it is going to another fluid domain. Okay. Convection heat transfer from outside surface to the oil. So, here convection will be happening. Okay. So, inside wall it will be conduction. Okay. So, from flame to wall, any solid body, normally convection and radiation will be playing role. Okay. So, common heat flux rate, water common heat flux rates. Okay. So, water like 10,000 design heat flux rate BTU per hour feet square. Okay. So, glycol you have seen, right, previous lectures we have seen 7500. Again amine, it is 7500. Okay. So, just some rough value, so that you can get some idea what will be the heat flux rate. Okay. Required fire tube area, fire tube equals heat duty including losses BTU per hour and design flux rate. Okay. So, we will try to calculate some electrical analogy, electrical analogy or analogy. Okay. So, let us say one heat transfer surface is like this and you have 3 layers of metal, let us say copper, aluminum, iron. So, one layer will have conductivity Ka, this is A metal, this is B metal, different heat transfer conductivity Kc. Okay. So, 3 different metal I have taken and temperature, let us say T1, T inlet or T outlet, or T inner surface, T outer surface. Okay. And T1, T2, T, then length or thickness of the metals x1, x2, x3. Okay, the distance. So, if T1 is high, let us say 100, this is 10. Okay. So, initial Ka, okay, temperature higher, after metal Ka, T2 temperature will be like this, Ti, T1, not T2, T1, and then maybe T2, then maybe T3 or TO. Okay. So, if thermal conductivity equal, then it will be straight line. It is not equal, so that is why it can curve will be different. Okay. Now, what is the heat transfer rate from A, B, C, D, A to B? A to B heat transfer rate equals minus Ka delta T by L equals minus Ka area. What is the area? Area we assume 1. Okay. Let us say area equals 1 for all cases. surface area, this area actually. Okay, this surface area 1, del t equals Ti minus T1 and L means x1. Okay. Now let us say QAB, QBC minus KB into A1. So del T again T2 minus T1 minus T2 x2, QBCCD equals minus KC T2 minus TO divided by x3. Now all the heat flux actually equal. QAB equals QBC equals ABBCCD, QCD equals Q. All heat flux equal because there is no energy loss, we are assuming. Okay, so there, because of energy conservation, so all heat fluxes are equal. Now del T1 A to B surface temperature difference, Ti minus T1 equals QAB by Ka, T1 minus T2 equals QBC Ka, T2 minus T3 QCD by Ka. If I have A value instead of 1, then I will have A also, area also. Okay. So now if I add 1, 2, 3, if I add 1, 2, 3, then it will become like Ti minus To equals QAB 1 by Ka plus 1 by Kb plus 1 by Kc. X will be also coming. X will be coming, x2, x3. So x1, x2, x3. Okay. Now QAB equals Q actually. So Q equals del T divided by XA by Ka plus XB by Kb plus XC by Kc. Okay. So del T equals del T. Del T I assume equals del Ti minus To. Okay. So Q is coming like this. Now if I make it electrical analogy, R thermal resistance, R equals thermal resistance equals del X by K, or X by K, or del X by K. Okay, I write K, X by K. Now if I make thermal analogy, so Ti, T1, T2, To. So this is Ra, Rb, Rc. Okay, this is Ra, this is Rb, this is Rc. Okay, R conductivity equals del Xn by K Na area. So Q equals Ti minus To R1 plus R2 plus R3. Okay. So whenever you are creating electrical analogy, so I will be implying as a Q, heat transfer rate. Okay. Resistance already you have seen here, R resistance we are showing, and voltage temperature difference. Voltage will be del T actually, temperature difference. So temperature difference high, more current will be passing. Okay. So this way you compare electrical system with thermal heat transfer system. So heat transfer through radial pipe. So I have pipe like this. Okay. So HT through radial pipe. So in that case, Q equals minus K 2 pi R L dt by dr. Okay. So T equals Ti at R equals Ri equals To at R equals Ro. Okay. Now if you analyze properly, like this, you take only one phase. This is Ri, Ro radius, this is thermal conductivity K. So Q equals minus K dt by dr 2 pi RL, 2 pi RL. So Ri, Ro integrating dr by r equals 2 pi RL Q dt To Ti. So therefore Q will be coming K 2 pi RL Ti minus To logarithm of Ro Ri. So Q equals K Al Ti minus To Ro minus Ri. So A 2 pi L Ro minus Ri logarithm of Ro Ri. RL Ro minus Ri logarithm of Ro by Ri. So Ti, T1, T4, you can say T2, T3, T4 or T. Okay. So this is logarithm of R1 by R2, 2 pi K A L logarithm of R3 by R2, 2 pi K B L R3 by R4, 2 pi K C L. So Q is coming 2 pi L T1 minus T4 logarithm of R2 by R1 Ka plus logarithm of R3 by R2 by Kb plus logarithm of R4 minus R3 logarithm R4 by R3 divided by Kc. So this is the formula coming. If I have multiple layers T1, T2, T3, T4, okay, R1, R1, R2, R3, R4, okay. So outside temperature T4, inside temperature T1. Okay. So if you have multiple layer, then this will be your general formula for radial heat transfer through pipe. A circular tube transports hot fluid given data Ro 0.5, Ti 80 degrees centigrade, Ro 0.4, outer temperature 25 degrees. So, first you draw pipe. Okay. So, pipe Ri is given Ro. So, Ri given 0.4, Ro given 0.5, K value is given 10 watt per meter K. So, Q per meter length you have to calculate. So, formula is that Q per meter equals K 2 pi L T I minus T O logarithm of R O by R I. So, the value is like 10 2 pi L 80 minus 25 by logarithm of 0.5 by 0.4 equals 15487 watt per meter. So, this is the solution. So, another problem, two plates of equal thickness. So, equal thickness T cross sectional area from composite heat transfer medium, thermal conductivity of K and 2K. Effective thermal conductivity of the composites K effective you have to find. So, for steady state heat transfer, total resistance R1 plus R2, okay, resistance actually, and R resistance equals T by K. So, area and thickness equal, A, let us say this is A, this is B, area A and area B equal, and thickness also equally given. So, total R is becoming like 2 T by K effective. So, R1 T by K, R2 T by 2K. So, therefore, T by K equals 3 T by 2K, 2 T by K. So, this one and this one, it will come like this, 4 3 by K. So, problem we have taken from GATE 2017, an oil emulsion having 15% water cut. So, water cut 15% by weight is being treated in a horizontal heater treater. You are using and oil emulsion flow rate is 6000 kg per hour. Okay. So, how much water is there? So, 15% water actually, 6000 water plus oil is 6000. So, 15%, 6000 into 15, so 900 kg per hour. So, Q oil, this is Q water I can write, Q oil equals 6000 into 0.85. So, it is going 5100 kg per hour. Okay, oil and water percent amount we got. The inlet temperature, T inlet temperature of the emulsion 30 and operating temperature heater 40, T operating 40 degrees centigrade. The specific heat capacity C for water, C for oil 0.5, C for water 1. Assuming 10% heat input loss, 10% loss. Okay. The total heat energy required to break the emulsion, total heat energy, HE, heat energy I am writing like this, how much will be heat energy. Okay. So, water cut we got, oil flow rate we got. So, 0.9 heat energy equals heat oil plus heat water, heat oil, heat water. So, how much it will be, like 5100 into oil 0.5, temperature increasing 40 to 30, yeah, temperature increasing 30 to 40. So, 40 minus 30, so that I will get positive value, plus 900 into 1 into 40 minus 30, same temperature actually. So, this total is coming 34500 divided by 0.9 equals 38333.3 kcal per hour. Okay, so this much of heat energy should be input. So another problem from GATE again. Saturated steam 0.5 atmospheric pressure and 90 degrees centigrade condenses on a vertical pipe 2 centimeter outside diameter. Vertical pipe 2 centimeter outside diameter, 2 centimeter, 40 length. The average conduction heat transfer coefficient K given 1200 watt per meter square K. Outside surface temperature T surface temperature given 85 degree. The enthalpy values are given H steam and steam 2660 kJ per kg. You should remember the unit kJ per kg. H condensate liquid 375. Okay, so enthalpy values are given, internal energy you got. So how much energy you have given, actually difference of these two amount, that much of energy you have given actually. Rate of his steam condensation you have to calculate. Okay, so Q equals UA del T mean temperature increase. So U 2 pi RL del Tm equals 12,000 U value given into 2 pi into 0.101 R is given into del Tm 0.4 no, this L 0.4 and then del Tm 90 minus 85. So it is coming 1507.96 watt. So enthalpy change happened. So total heat given. So let's M is the rate of condensation. Okay, so rate of condensation is M into 2285 into 1000 divided by 3600. Actually 2285 is coming like this. These two difference is giving 2285 kJ per kg. So kJ kilojoule is there, so that's why 1000 came, and hour is given, that's why 3600 came. So it is coming 1507.96. It is given calculated from here. Okay, so therefore M equals 2.375 kg per hour. Okay, this is the answer. This is the simplest problem in a parallel flow heat exchanger. Parallel flow heat exchanger, first we draw parallel flow. Parallel flow means like one going, one down. Hot fluid enters 100 and leaves 50. Cold fluid enters 30 and leaves 40. If heat losses are ignored, then LMTD. So this is very direct question actually. LMTD equals del T1. How much del T1 equals 100 minus 40 equals 60. Del T2 equals 50 minus 30 equals 20. So LMTD equals del T1 minus del T2 logarithm of del T1 by del T2. Okay, so 60 minus 20 by logarithm of 60 divided by 20. So this value will be coming 36.4 degrees centigrade. Okay. So if units are different, for example, inlet temperature, outlet temperature, if units are different or any unit different, then you have to convert into proper unit, then you try to calculate, otherwise you will get wrong result. So thank you very much for today's lecture. Next day we will start heat exchangers. Thank you very much.